Welcome back to CS 520. In this session I'm going to talk about floating point addition, and that's going to lead us into a brief discussion of the limits of floating point numbers. So floating point addition, again, it's this situation where you may have to think back to high school when you first thought about computing with numbers in scientific notation. If you were asked to add two numbers together like that, I can't just add the significands immediately because the exponents don't agree. I know I've got to bring those exponents into agreement. So I'm going to shift the smaller number over to the right. In this case, the exponents have a difference of 2, so I'm going to shift over 2 digits. And now my exponents are the same. Okay, and now I can go ahead and do the add, and again we can start to see the problems of floating point numbers. We don't know what those values are. Let me just add the other 3 digits though. And if for a moment we bring down the 5, 6, just assuming that those are zeros, although that's not necessarily true. Again, the numbers are approximations. We don't really know what those digits are out to the right. The 2.34 may have come from a balance that didn't measure accurately anything more precise. So we're just sort of fudging here. But what my high school chemistry teacher would have asked me to do probably is to use those numbers to round. And I would have rounded up because 5, 6 is clearly bigger than midway, and called this my result. Okay. Let's just review that algorithm that I just used. What did I do? All right, I shifted the significand of the smaller number to the right until the exponents agreed. Then I went ahead and added the significands. Note, this is just an integer addition. Let's go back to the example just to emphasize that. There's nothing magical here. When I actually added these numbers together, it was as if the radix point wasn't there. I just did arithmetic, right? Integer arithmetic. 4 plus 2 is 6, 3 plus 0 is 3, 2 plus 0 is 2. There's nothing magical about the floating point. So if I was going to implement floating point addition using only integer operations, I would be decoding the numbers, shifting the significands around, and ultimately I would be doing an integer add of the significands. Okay. All right, back to the algorithm here. The third step then after the addition is complete is I may need to normalize the result. So I might have a carry out the top, right? The addition, the result of the addition might have ended up with something like that. With 2 digits to the left of the radix, so I might have to shift back to the right. When I shift back to the right, I'm making the exponent bigger. When I make the exponent bigger, there's a chance for overflow, right? The exponent, there's a limited amount of bits in the exponent, and I may overflow those bits. The number becomes too big to be represented. The second thing that can happen is if in fact one of the numbers is negative and one is positive, I'm in effect doing a subtraction, and my result might be something like this. The numbers are close together. The numbers are close together. I end up with an unnormalized result because I have a lot of leading zeros. In this case, I have to shift to the left to normalize. Shifting to the left, I'm making the number bigger, so I have to bring the exponent down. When I bring the exponent down, subtract from it, that might result in underflow. I might end up with a number that's too close to 0 to be represented with the number of bits I have available for my exponent. So the normalization step can lead to both overflow and underflow. After I've normalized, then I may have some extra digits, and similar to what we looked at when we did the int to float conversion, I can use those extra bits that I can't fit into the 24 bits or 23 bits actually that I can store for significand. I can use those to round. I can use the round to even algorithm, for instance. Again, though, if I do need to round, I do need to add 1 to that lowest bit position, then that might cause me to need to do another normalization, because I could end up in this scenario again where I have a 1 being added way off to the right down here, and I get a ripple effect all the way across and a carry out to the left, which results in 2 digits to the left of the radix point, which is not normalized, so I need to normalize it by bringing it back to the right again. Okay. All right, let's work an actual example of adding together 2 IEEE single precision floating point numbers. So again, I'm doing this as we've done other examples. I'm looking at the bits. These are just 2 32-bit values, but I'm going to interpret them as IEEE single precision floating point. So step 1, as always, when doing these kind of problems, is I want to decode the 2 values. And again, I'm going to have to focus here, see if I can do this without making a mistake. This is when I need you guys in a live class to tell me when I do something wrong, but I don't have that luxury. Okay, that's the top number. Again, to decode, the key step in the decode is to find the exponent. It's right there. Let's go ahead and write the bits for the second number. Seven, 8F, 8, 7, 8, 7, 8, and the exponent is right there. Okay. First thing to note is both numbers are positive, so in fact I will be adding the significands together. Second thing to note is that neither exponent is a special case. Neither one is all 1 bits, indicating a nan or an infinity, and neither one is all 0 bits, indicating a 0 value or a denormalized value. Next step is, if you think about it, I don't really care what the actual exponents are. What I care about is the difference in the exponents, because that's going to tell me how much to shift the smaller value over. By the way, I can look at this, I can see the top number has the bigger exponent. So I'm going to be shifting the lower number. So I'm going to do binary arithmetic here, another risky proposition for me because I might make a mistake, but let me try it. I'm going to have to borrow 1 here. Again, I'm doing subtraction of these exponents. Okay, and I think I got that right. I subtract the 2 exponents, I get this in binary, which in decimal is 8, 4, and 1. That's 13 in decimal. So the change, the delta in the exponents, the difference in the exponents is 13. And that tells me how much to shift to the right, the smaller number. So let me write the significand of the top number first. Remember the 1, the leading 1 here to the left of the radix is not stored, so I have to remember to insert it as I decode. And now the bottom number, I need to place it 13 bits to the right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right, I'm going to place it 13 bits to the right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So the hidden 1 bit in the second number goes there. Then I copy in the stored significand. Okay, and I should end up with 13 bits out to the right, because again, there's a boundary here. I know in the result I can only store 23 bits plus the hidden 1 bit. which I don't store. So there's only 24 bits that I can keep around. So there's a boundary here, and I should have 13 bits out here to the right. 1, 5, 9, 13. Okay. Again, based upon our earlier discussion of this, we know these 2 bits are called the guard bits. And these bits are all summarized as the sticky bit. And since there's at least one bit out there, the sticky bit is equal to a 1. And we'll be using those to round, just like we talked about rounding numbers when we did the conversion from int to float. All right. At this point, I've got my 2 significands lined up, and I can do the integer addition. Here's my last risky operation. So 0 and 1 is 1. 1 and 1 is 0. Carry the 1. 0, carry a 1. 0, carry a 1. So 1, carry a 1. 0, carry a 1. 0, carry a 1. If I've done that right, then that's the result. And note the result is already normalized, so I don't need to do any normalization here. What I do need to think about, though, is rounding. I've got these extra bits, and it's a clear case of a round up because I've got something over 1/2, right? The guard bits are 1, 1. The sticky bit doesn't even matter. So I'm going to round up by adding 1 to that rightmost bit position. And my final significand is like that. Okay, now I'm ready to encode the final result. The sign, what's the sign of the result? The sign of the result is 0. I was adding together 2 positive numbers, so the result is going to be positive. What's the exponent of the result? Well, the exponent of the result, since I didn't have to normalize, I did not have to normalize, the exponent of the result is going to be the exponent of the bigger value. So what was that? That was 1, 1, 1, 1, 2, 3, 4, 0. It's a little hard to see because I had to do some carrying up here, but if I look at the original exponent before the subtraction, I think it was that. And then I need to write in the bits from the significand. Again, I don't store that bit, so I'm going to copy in 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 0, 0, 1, 1, 0, 1, 1, 1, 0. If I've done this right, then that's my final answer. Let me write down an answer in hex. So that's 7F 2A B 2 6 E. Let me just check 7F 2A B2 6E. It's a miracle. I made it to the end. The correct answer. Okay, so that illustrates the basic operations of adding together 2 floating point numbers. It also should give you a good insight into how you would implement this if you were going to do it in C with only using integer operations. All right, looking at integer addition gives us a good window into limitations of floating point numbers. And the big point is you have to remember these numbers are approximate. They're approximations of some realities, some physical reality. Because we only have a limited number of bits, we have to chop at some point. Okay, so first thing to realize is that floating point equality is problematic. Right? Both these numbers are approximations, so there's some fuzziness to both numbers. So asking them to be exactly equal doesn't really make sense. What you really need to think about is whether this value, the difference in this value, is less than and some, some epsilon. Are these numbers close enough together that you consider them equal in your application? That's really the mindset you've got to get into. You've got to remember that these are approximate values. Another thing that can show you the problems with floating point. Consider again back in decimal now, base 10. If I do this subtraction, what do I get? Well, the exponents are already the same, so that's fine. All right, I end up with that. It's not a normal form though, so I would normalize that. But the question is, as I shift to the left, 1, 2, 3, 4 positions, what am I going to do here? I'm bringing in stuff from the left. I'm bringing in stuff from the right. I don't have anything out to the right. Okay, so I don't really know what those bits are. What's the exponent? I shifted over 4, so I guess I have to decrease it by 4, right? And maybe I put zeros in there, but I don't really know. Those are they are really just garbage. I may have gone from having two numbers that had 5 digits that actually match reality, but when I get done with the subtraction, I've only got 1 digit that's tied to reality, and I've got 4 digits that I'm just pulling out of thin air, right? They came from to the right of these two values, and I didn't even know anything about what's out to the right there. My balance didn't weigh that accurately, or whatever the physical reality is. And all of a sudden I'm carrying around zeros here that really are not meaningful. Okay. So doing subtractions in floating point applications of two numbers that are close together is problematic. It often leads to loss of accuracy of your values. Another thing that points out the trouble with floating point calculations is that floating point addition is not associative. Let's look at 2 ways of adding 3 numbers together. Right, if I group them right to left, first of all, I'm going to have this one being added to, if you just think about this, what happens if I add 1 to a very large number? Well, I'm going to, when I go to align these, I'm going to shift the 1 way out to the right, too far to ever be seen again. The result of the addition will simply be I add 1, but I get the same value back. So that when I get done and add the final 2 values here, I get 0 here. On the other hand, if I group it the other way and I add the 2 values of similar absolute value together, they're going to cancel. And now I add in the 1, and the 1 can still be seen. So the order in which I do these operations can impact the results. Okay. All right, well, I'm just trying to give you enough understanding to make you aware that you don't know enough about floating point calculations to be competent writing floating point applications. Okay. You really need to learn more. I've just taught you how they're encoded, but I haven't taught you how to be carefully about your structuring your floating point applications. And really, it's a math course. You want to study numerical analysis, which is Math 753. If you get to take that here at UNH, that's great. But if you don't, and your boss comes to you someday and asks you to be involved in writing a floating point application, you want to be humble. You want to tell the boss the truth and say, I don't think I know what I know. I have what I need. I don't have what it needs to do this. Please let me take a course in numerical analysis first. Okay. Unfortunately, there's a whole series of disaster stories out there about poorly written floating point applications. For one disaster story, just Google the Ariane 5. Okay, so the takeaway here is I didn't teach you everything you need to know to write floating point applications. Keep that in mind as you move forward with your career. Let's stop here.